Ready to start. So our speaker today is Max Engelstein, and he's going to talk about winding for wave maps.
Thank you very much, Camillo, and thanks for the invitation. This is a great excuse to put on a collared shirt. It might be the first time I've done so in 3 months or so. Okay, so I'll talk about winding for wave maps. Maybe 2 caveats. One, this is the first Zoom talk I've given, so forgive me if I make some sort of basic mistakes. And please feel free to ask questions. I'll try to monitor the chat, but I can't promise I'll be great at that. And the second is this is the first talk I've given on wave maps. So forgive me if I've omitted your seminal work on the topic. I've tried to cite everyone correctly, but you always miss things. Okay, so winding for wave maps, all of this is joint work with Dana Mendelsohn, who's an assistant professor at the University of Chicago. Okay, so what's the point of this talk? I'll sort of give you a quick outline, so that way you can turn off your video and do dishes and not really pay attention for the rest of it, and that'll be fine. So we'll be talking about wave maps, which are wave equations, but the values are constrained to lie in a manifold. Or, if you prefer to think about elliptic things, these are harmonic maps, but the domains are Lorentzian, right? So there's a time, and the time is weighted with a negative sign, whereas the space is weighted with a positive sign. And we're going to be looking at energy critical wave maps. We'll talk more about what this means, but in particular, this means that energy can concentrate in small scales in space and time. And so when you zoom in at those points, you'll get a weak sequential limit, which is called a bubble. It's a harmonic map. And the basic question is, does this bubble depend on the sequence of rescalings, right? So obviously you could get different bubbles at different points, but because you're only getting this bubble out of some compactness theorem, it's also possible that when you scale in at different scalings, you get different bubbles. And this is the question we're going to try to address. And in fact, we construct an example, which we think is the first example in sort of the dispersive PDE realm of non-uniqueness of this bubbling. So you zoom in at 2 different centered around the same point in space-time, but along 2 different sequences of rescalings, and you get 2 different bubbles. But what's the catch? The catch is that the target is non-analytic, right? So usually when you think about sort of the target, you're thinking about something very nice like a sphere. This is not going to be so nice. And the inspiration for all of this is Topping's really beautiful work on harmonic map heat flow. But I hope to convince you that somehow it's a little bit surprising that you can take this lesson from the parabolic setting and port it to the sort of Hamiltonian or dispersive setting. These are very different types of PDEs.
Max, can I interrupt you with a question?
Of course. Yeah.
So are these non-uniqueness examples related to the one in the elliptic case by Brian White?
Yes, very much so.
Okay.
So Topping's example, I think, came out around the same time as Brian's example. And they're all sort of the same example. We'll talk about that a little bit later.
Okay.
Okay, so let's start really basic. What are wave maps? You have some U, it goes from R1 plus D. The 1 is for time, the D is for space, and it goes to some manifold, M. And you should think of them as being critical points of this sort of Lagrangian energy, right? Where you take the spatial gradient and you subtract the time gradient. And I write this sort of sub G here to talk about the metric, but I'll probably forget about it half the time, so apologies. What's important is that this has no coercivity. This is not an elliptic minimization problem here, right? Because there's this negative sign, which is quite annoying. And you could have purely time critical points for these things. So what we do is we do the Cauchy problem. We prescribe some initial data on all of RD. And if the initial data is really nice and smooth, it's sort of a graduate PDE exercise that a solution should exist and should be smooth for short time. There's also a lot of really difficult and very seminal work for rougher initial data by Kleinerman and Selberg and Kleinenberg and Machadon. But we'll be looking at smooth initial data, so don't worry about any of that. You can write this in coordinates. I don't know. If you're better at manifolds than I am, maybe this equation sort of tells you something. These symbols here are the Christoffel symbols. But to me, this is not a particularly illuminating equation. I guess what's important, of course, is that it's sort of a wave type equation, right? And why would you study these wave maps? Well, when d equals 1, this is exactly the equation you get for geodesics. So if you like to think of geodesics as being how a point naturally evolves in a manifold, you could sort of think of wave maps as being how higher dimensional things naturally evolve in a manifold. This is sort of a natural nonlinear wave equation to consider. It's a natural geometric flow. There's been a lot of really great recent work which sort of gives geometric information by looking at parabolic flows on that manifold, like the Ricci flow, for example. And you might hope that if you understood wave maps a little bit better, you could also learn some important geometry about the target. Okay, now I'll talk about two things that I know nothing about. Apparently, these are simplified models for Yang-Mills flows. Who knows? This is what everyone says. And if you have a model of general relativity where there are two killing fields, this is also encapsulated by the wave maps equation. So people care about these equations. They're interesting, apparently. Okay, but let's specify to an important example, right? We're going to ask the target to be a sphere, and we're going to ask the domain to be two-dimensional. And here, the equations sort of simplify to something a lot easier to understand. You should think of as vectorial, right? It's going into the sphere. And so here are the equations. And if you make an additional symmetry assumption, which is that the solution to the equation respects the symmetry of the target manifold, then you can simplify the equation even more. So these U's, where you think of, they just sort of, oh, okay. Let me draw you a little picture. So here you have the plane, and then you have a sphere, which lies on top of the plane. And you should think of these U's as just sort of wrapping the sphere, the plane, around the sphere, right? So this angle is what I call alpha, and this angle is what I call theta. So the equivariant wave maps leave theta the same, and then sort of radially wrap the plane around the sphere.
Max, one quick question, if I could.
Of course, Dallas.
So it's R1 plus D, and is D always the same dimension as the target manifold?
It doesn't have to be. And in fact, later in the talk, it won't be. We're very soon going to specify to D equals 2. This is an important dimension for reasons of energy that we'll talk about in a second.
Thanks.
Of course.
I want to point out that was Yash, not me.
Oh, sorry. Somehow you guys sound, Yash's Zoom voice sounds a lot like Dallas's in-person voice. I don't know. Sorry, Yash.
No, don't worry about it.
Okay, are there any other questions? Okay, great. So at the bottom is the equation for sort of alpha, right? The azimuth angle, I think people call it. And you can see that it's sort of a lot easier to get a hands on, right? This term here is the sort of spherical Laplacian, if you'd like. And just this part is the radial Laplacian. So you can think of this as sort of being the second derivative in t minus the radial Laplacian plus some sort of non-linearity. And this is often a nice way to think about it. Okay, so let's keep thinking about this spherical example, and we're going to sort of reduce the equivariant class. And there's one particular solution, which is really nice. It's time independent. So for any lambda not equal to 0, I guess for lambda equal to 0, but then it's not that interesting. You can define this, which has a very explicit formula, and which solves the wave map equation, but is time independent, right? So there's a secret dtt squared q here, but this is 0. For those of you who sort of are unfamiliar, this q is what's called a harmonic map. And it's basically a critical point of just the space energy, right? So you look at maps that go from R2 to S2, and then you sort of try to minimize or look at critical points of the energy, the sort of Dirichlet energy of these maps. So any harmonic map is sort of automatically a wave map, which is time independent. And that's an important point. This is actually the lowest energy harmonic map from R2 to the sphere, which is not trivial. And that's also going to play an important role. So maybe I'll write that. Lowest energy, non-trivial. Cool. So there's this beautiful theorem of Krieger, Schlag, and Tataru from 2008, which says that you can actually write an equivariant wave map from R2 to the sphere, which is this Q suitably rescaled in time, plus something that you might call an error term. Although error is sort of wrong because it doesn't go to zero, but it goes to zero on any compact subset of time. And what's really interesting is that this lambda is getting really small as t goes to zero, and you're dividing by it. So in particular, this exhibits what's called blowup, right? This u is smooth as you sort of go down to time equals zero, or up to time equals zero, whatever you want, if time flows backwards or forwards for you. But at time equals zero, it's obviously not smooth. Oh, I lose my markings when I change the slides, so I'll put those back here. There's also very nice examples of what are called finite time blowup in other wave map equations by Raphael and Rodniansky and Sturbins. So this was the first example of demonstrated finite time blowup, where you have a solution which is smooth and then develops a singularity, right? So this develops a singularity at sort of the point 0, 0. And we'll be talking about blowups today. So we'll talk about this example quite a bit. Cool. So to understand this example better, it makes sense to define what's called the energy. And it turns out that if you have a wave map and you add the spatial gradient and the time gradient, that this sum, when you integrate it over all of space, is constant in t. So for those of you who are sort of more familiar with the parabolic settings, right, you would expect the energy to sort of decrease strictly in time as you go along the flow. But here the energy is conserved. And this is sort of a simple computation. You can differentiate this in t and then see that it should be equal to 0. Just by rescaling the equation, you can see that if u is a wave map and then you multiply both space and time by lambda, you also get another wave map. And the energy scales like this. And this exponent is important, right? It tells us that when the domain is dimension 2, then the energy is invariant under scaling, right? So these are often called energy critical wave maps. So in particular, if we remember our q lambda is equal to 2 arctangent of lambda r. You can see my handwriting and appreciate the fact that I made a slideshow as opposed to a board talk. This energy is the same for all the q lambdas. So if you think about the Krieger, Schlag, Tataru example, its energy is not blowing up as t goes to 0. But what's interesting is that if you look at smaller and smaller neighborhoods of the point 0, 0, its energy is not going to 0, right? So this is what's called energy concentration. Energy concentration. And this should be a familiar example to people who have worked with things like harmonic map heat flow or harmonic maps. In fact, it's a pretty pervasive example, like sort of generally in energy critical equations, that you can have this sort of bubbling or energy concentration. Great. Cool. So let's look at more examples. We have this Krieger-Schlag-Tataru example, but it's also possible that you can sort of concentrate at time is infinity. So there's a very nice recent preprint by Pillai, which shows that you can do this Krieger-Schlag-Tataru concentration as time goes to infinity. And actually, he gets a whole rate, or sorry, a whole continuum of different rates that you can concentrate energy at. I want to talk a little bit about this idea of scattering. So here, the error satisfies a linearized wave equation as time goes to infinity. So if you'd like, you can think that you can break U up into a part where the energy is concentrating, and then a part where the energy is dispersing it sort of as much as possible. You can also get two bubbles which concentrate at the same point in time, right? So there's this beautiful construction by Gendry, who shows that as time goes to infinity, you can get two bubbles, one of which is sort of staying at scale 1, and the other of which is staying at scales which are going to 0. In the harmonic map heat flow literature, these are often called bubble trees, although wave map people don't call them that. You might be annoyed by this exponent k, right? We've been just dealing with regular arctan, so why are we looking at arctan of r to the k? The statement is just a lot easier when you look at sort of arctan of r to the k, which you should think of as sort of like being how many times you're sort of wrapping around the plane over the sphere. But there is a result for k equals 1, which is our usual arctan. And then maybe something which is quite interesting is that there's actually a rigidity in this exponent. So recent work of Gentry and Laurie showed that it has to be this sort of exact exponent, and they actually get a coefficient in front of it, at least as long as the energy of U is equal to the energy of two bubbles. So this is quite cool. And in all of these examples, what do we see? Well, we could rescale our bubble, and then if we take a limit as the time goes to the time of bubbling, what will we get? But we'll get a Q. Sorry, I said rescale our bubble, but I mean we can rescale our solution to the wave map equation, right? So all we're doing is we're sort of taking this and moving it to U of RT. And then as we take a limit, what we'll get is we'll get exactly this Q, which we call bubble. And so this process is called bubbling off a Q. Great. Are there any questions here about this energy concentration? Cool. Fantastic. So we'll keep going. Okay. So we can see that this energy concentration prevents smoothness. And it turns out it's a very beautiful result of Sturbins and Tataru that this is the only thing that prevents smoothness, essentially. So if you're at a particular point in space-time, either you can have energy concentration, and I'll talk about this light cone in a second, or you can continue the map smoothly. And if you have a concentration, then if you rescale your solution, you get a bubble, you get a harmonic map. So what do I mean by this light cone? Oh, let me just push forward. There's also an infinite time version, which I'll talk about in a second. So this is my point, x0, t0. And these are lines of slope 1, right? And I'm drawing this direction is time, this direction is space. And so as you move inside these light cones along time slices, what can happen is either the energy is non-zero in the limit, in which case you expect to have a bubble, or the energy is 0 in the limit, in which case you can expect to smoothly continue your solution. And there's also an infinite time version where you look at still t and x, and now you sort of look at the energy of these time slices as t goes up to infinity. And you should expect that one of two things happens. Either the energy sort of disperses as if it were almost a solution to a linear wave equation, or the energy concentrates inside of this light cone. And then we still say it's bubbling, even though it's not necessarily concentrating at infinitely small scales, right? Think about the example of Gendry with the two bubbles. One of the bubbles wasn't sort of concentrating on infinitely small scales, but it was concentrating at constant scale as we went up to time equals infinity. And we're still going to call that bubbling. Cool. Are there any questions here? So this is nice, right? It tells you that this is basically the only thing that can go wrong, which makes it a good thing to study, this bubbling. So let me talk a little bit more about this theorem. For the rest of the talk, I'm going to ignore this thing which I sort of elided over earlier called the Lorentz transform. It's a natural symmetry of the equation which sort of pairs the time and space direction, and it will just complicate this whole discussion. So I'm just going to ignore them. But a real treatment of this would have to talk about them. If for some reason you can rule out bubbles, then you actually get a long time existence and smoothness result. So there's lots of beautiful work by Krieger, Schlag, Struve, Tao, and Tataru, which rule out the presence of bubbles either by some hypothesis on the target, right? For example, if it's a hyperbolic manifold, then maybe you can say that it doesn't admit any harmonic maps. And so then this sort of second aspect of the dichotomy can't occur. Or by hypotheses on the energy of your solution. If the energy of your solution is lower than the energy of a non-trivial harmonic map, then you can't bubble off a harmonic map. And so you are always smooth, right? So let me sort of write this here, energy topology. Another corollary of this sort of interesting fact is that if you develop two bubbles at a particular time and space, then the sequences of rescalings at which you see the two bubbles must be completely non-interacting, right? So if sort of u of xn plus snx, tn plus snt converges to omega 1, and u of xn plus rnx, tn plus rnt converges to omega 2, and omega 1 is not equal to omega 2, that must mean that Rn over Sn goes to 0 or plus infinity. So the scales are non-interacting with one another. So you can get multiple bubbles. We saw that in the example of Jacek Gendry, but these two bubbles can sort of not interact after the weak scaling. Great. And so what's the big question here? Does the bubble depend on the sequence of times that we take, or the sequence of rescalings, right? And to make this a little bit more formal, do there exist continuous rescaling and translation parameters such that this limit occurs as t goes up to your time t max? So I hope this sort of basic question is clear, but of course, if it's not, you should ask me to clarify. Maybe I'll take a second to let you guys internalize it, if you will. Okay, if there aren't any questions about this, then I'll keep going. I can't see any of your faces, so you'll just have to speak up if you have questions. Great. So one issue with talking about uniqueness of this bubbling in the wave map setting, as opposed to, say, uniqueness of tangents in an elliptic problem, is that different bubbles can appear at different scales. And so you might have a situation where one of the bubbles is unique or one of the bubbles isn't, or if you choose the scales incorrectly, you could see one bubble sometimes, but another bubble another time, right? So you can see how these multiple bubbles make the question of uniqueness a little bit harder to state formally. So this is sort of captured by what's called the Soliton resolution conjecture, which originated in works of Fermi, Pasta, and Ulam in the 1970s, I think. They were looking at models of fluids. And sort of similar numerical models have exhibited this type of bubbling when looking at lots of different physical phenomenon. So this is something that physicists sort of first came across, is my understanding. So what's the idea is that if you have energy concentration at a point in time, then you should bubble off a bunch of harmonic maps. These harmonic maps should develop at scales which don't see each other, but which are all smaller than the light cone scale, right? So remember, the scaling here is sort of this slope 1, right? So this width is T0 minus T. And we expect these scales to be much smaller than that. And so after you rescale appropriately, you expect your solution to look like a sum of these bubbles plus some smooth term, which is sometimes called radiation. So this is the Soliton resolution conjecture, right? And as you could see, it sort of, it formalizes this idea of uniqueness of bubbles, but not just one bubble at one scale, but all the bubbles that develop at all the scales.
Max, quick question.
Of course.
Is there supposed to be like an upper bound on the number of bubbles you might get?
Great.
Be infinity.
Great question. So the energy of U, which remember is constant in time, will be equal to the sum of the energy of these QJs plus the energy of phi. So since this is a finite number, and since, okay, so there's a fact about harmonic maps, which is either they have 0 energy or they have epsilon naught energy. You can't sort of get arbitrarily close to 0 energy as a harmonic map.
Got it.
So that immediately tells you that there have to be finitely many of them. But that's a really good question.
Right.
And but then how many of them there can be depends on the energy of the U, right?
Yeah. And then I guess sort of a follow-up is there, you said there's this epsilon naught, which is this lower bound on the energy of harmonic maps.
Mm-hmm.
Somehow quantified in some way?
Epsilon naught depends on epsilon naught depends on the target manifold, very much so.
Okay.
Is it quantified in some way? I mean, there are manifolds that you can compute it for, but I don't think that there's some universal epsilon naught that works for all manifolds. Maybe that doesn't answer your question.
No, it's good enough answer. Thanks.
Okay. Yeah, this goes back to work of like Sachs and Uhlenbeck and Schoen and Uhlenbeck and stuff like that.
Cool. Thanks.
Yeah. Yeah, so maybe some remarks on this Soliton resolution conjecture. So there are analogs for a lot of sort of nonlinear wave equations. KdV, the nonlinear Schrodinger equation, Yang-Mills. So this is sort of a family of conjectures, if you'd like. This version that I've written here, I don't know why I have this highlighted bit, I'm sorry, is simplified. So I've eliminated these Lorentz transforms that I alluded to before, and I've also eliminated the fact that this sort of x0 could depend on t. You know, to write the conjecture out in full generality is really quite difficult, and we're about to make some symmetry assumptions, which will sort of rule out a lot of these potential complications. So don't worry about that too much. This sort of captures the spirit of the conjecture. So let me just say that there's been a ton of work on the Soliton resolution conjecture in lots and lots of different settings, and I can't talk about all of it, mostly because I don't know all of it. So let me very much specify to work on the Soliton resolution conjecture into for wave maps into, so this is when n is a manifold of revolution. So like the sphere or something like that. So it has this sort of symmetry. So oftentimes people are able to prove the Soliton resolution conjecture not over full times, but rather over a sequence of times. So you assume there's sort of a Tn here, right? And Tn is going up to T naught. And then, of course, that still leaves open the question of whether or not the bubbles depend on the sequence of times. So here there's very nice work by Coate, who proved sequential Soliton resolution into the sphere, but with some symmetry assumptions. Grinnis, who proved the sequential Soliton resolution into the sphere, but without the symmetry assumptions. And then John Koenig, who also proved sequential Soliton resolution into manifolds of revolution, but with symmetry assumptions. There's some work in the continuous time, but usually the continuous time setting needs very strong extra assumptions to sort of simplify the space of bubbles that you could be looking at. So for example, there's this work of Gendry-Lowry, which I talked about before, which assumes that there are two bubbles and that your energy is exactly the energy of two bubbles. There's also some nice work of Coate, Koenig, Lowry, and Schlag, which assumes that your energy only allows for one bubble, right? And then there's work of Ducaetz, Ja, Koenig, and Merle, which also assumes that your energy only allows for one bubble. So usually if you can prove this full Soliton resolution, it's because you've sort of made an extra assumption that vastly cuts down on the number of different bubbles that can show up. So let me just talk a little bit. So I'm gonna give you some notation. En is gonna be the energy of the lowest non-trivial, harmonic map into n. So if you assume that the energy of your U is less than En plus epsilon, you can guarantee that you only can develop one bubble by exactly my answer to Yash's question earlier, right? The sum of the energy of the bubbles has to be equal to the energy of U. So this is often called the ground state energy. And oftentimes people like to make the assumption that their energy is just barely above the ground state. So that allows for the development of a bubble, but doesn't allow for the development of too many bubbles. Okay, so this is a big conjecture. Lots of people work on it. And yeah, there's lots of work in a variety of settings. I'm sorry that I'm not studying it comprehensively. But now let me get to the main result of my talk. So I proved with Dana, and we just put it up on the archive on Friday, that there exists a smooth, up to the bubbling time, symmetric wave map. It goes from R1 plus 2 to N. I can tell you what the manifold is. It's a warped product of a torus and a sphere. And at the origin and at the bubbling time, it develops a continuum of different bubbles. So you can get infinitely many different bubbles depending on the sequence of times you take up to the bubbling time. Okay, so immediately, this implies that the Soliton resolution conjecture doesn't hold for wave maps into this manifold, right? You can't get a full time expansion like the one we had on the previous slide if you develop a continuum of different bubbles at the origin. Ooh, there's some stuff in the chat. Okay. Yes, D equals 2. That was a while ago, sorry. And then the energy spectrum of the bubbles is continuous here. This is a good question. If you're asking about a general target manifold, it's not necessarily true that you have a continuous energy spectrum of bubbles. And for our particular manifold, I guess I'll get to this soon. So the energy of U is going to be less than the ground state for N plus epsilon. And in particular, we can show a gap above the ground state. So the energy spectrum is not continuous for our particular N. So there's sort of the next energy of the next harmonic map has larger energy. So sorry, those were questions from the chat. Wow, this is completely incomprehensible, huh? Let me try to write this out.
Hey, Max?
Yes.
Well, I guess maybe Stephen was wondering, because you have continuously many of them, right? So they all have the same energy because of this factor T2. Is that the point, right?
Yes, that's exactly right. So what's very important is that there's a continuum of harmonic maps at the same energy level. And this is what allows us to do what we want. And this sort of richness of the space of harmonic maps is going to be the key in our proof. That's absolutely right, Stephen. Okay, so the proof actually gives you a family of solutions which exhibit this non-uniqueness, but this family isn't necessarily stable. So we can't sort of tell you if this is a generic phenomenon or not. And I can tell you what I mean by symmetric. So these can't be equivariant wave maps because the target's not a sphere, but they're very close to equivariant. So the first component is radial. It depends only on R. And the second component is equivariant, right? So it does this wrapping around thing that I talked about before. Great. We're going to call this quasi-equivariance because it needs a name. And we're not particularly creative. And this is what I was talking about before with relation to Stephen's question. So the energy of our solution is right above the ground state, but I'm lying to you a little bit. Our manifold is kind of complicated, so I actually can't tell you what the energy of the lowest non-trivial harmonic map is. But En is the smallest energy of a non-trivial quasi-equivariant harmonic map. So it's the smallest energy in this symmetry class. And since the bubbles that you develop have the same symmetry as the initial equation, it's sort of the smallest admissible energy, if you'd like. So I'm going to call this the ground state, even though that's sort of abusing notation. And I'm pointing this out for the following reason. All of the uniqueness, all of the Soliton resolution proofs that we have so far have worked under symmetry assumptions or under energy assumptions, right? You assume that you have something that's radially symmetric, or you assume that you have very small energy that allows for only one bubble. And what I'm telling you is, here we have an example where Soliton resolution doesn't hold, but it's not because we're doing anything fancy with the energy or the symmetry. This is pretty much the simplest symmetry that we could consider. And this is pretty much the simplest energy that we could consider. So the non-uniqueness is not coming from there. It's coming from something else. It's coming from this warping factor, F. Okay. So now it's time for me to say that this theorem, and in fact our entire proof, is really inspired by work of Peter Topping on harmonic map heat flow. So let me talk a little bit about Topping's work, and then I'll compare sort of the two ideas. I should hurry up a little bit. So harmonic map heat flow is the gradient flow of this energy, right? We talked about this before when we were talking about harmonic maps. You can write the equation. It looks a lot like the equation for wave maps, except you only have one time derivative, not two. And the main theorem in Topping feels a lot like the main theorem that I just told you on the last slide, which is that you can have a harmonic map heat flow, which goes from here, this ball lives inside of R2, to the same manifold n. And it also develops a continuum of different bubbles at the origin as t goes up to t max. Camillo asked this question at the very beginning of the talk. This is a very similar example to Brian White's example for non-uniqueness of tangents for harmonic maps. And then Peter Topping has a very similar example for the non-uniqueness of the long time limit of harmonic map heat flow. So as time goes to infinity. Topping's paper also gets rates on, gets bounds on the rates of bubbling and the first time of bubbling. We can't do that in our setting, and this is because harmonic maps have a lot more coercivity to them than wave maps do. I'll talk about that more later. And he introduces a mechanism of proving this non-uniqueness, which is called winding. We use the same mechanism, and I'll talk about this more later, but right now I just want to say that if you think about it a little bit, showing that a bubble is non-unique is actually really hard, right? Because all the approaches we have for showing that something bubbles sort of use ODE techniques and such, and sort of require that the solution bubbles in this way, which will give you uniqueness of the bubbling. So it's kind of difficult to come up with an idea that shows you that something is non-unique. This is a very beautiful paper by Topping, in my opinion. Okay, so what's behind this result of Peter Topping? Well, if you work in parabolic and elliptic problems, you should be thinking that flows for analytic functionals often have unique limits. And this is due to the Voya inequality. So this is an inequality about analytic functions on Rn. It says that if you have a critical point of an analytic function, then you know the growth of the function, in particular the growth of its gradient, near the critical point. And as a corollary, you can say the following. If you have a gradient flow of a non-analytic function, of an analytic function, and this gradient flow is bounded as t goes to infinity, then its limit as t goes to infinity exists. So it has a unique limit. You can have many different limit points. It's sort of a little tricky to go from here to here, but it's really, I mean, it's elementary in some sense. You just need to know what to do, which maybe describes a lot of mathematics. I don't know. So a little bit of background, because it's kind of fun. Voya didn't care at all about parabolic flows. He was a real algebraic geometer who cared about the locus sets of analytic functions, essentially. And then Leon Simon in '83 realized that you could use this finite dimensional Voya inequality to tell you something about the gradient flows of elliptic functionals. And so these Simon-Voya inequalities have been used a ton all over the place to show the uniqueness of either infinitesimal behavior or long-term behavior of flows in elliptic and parabolic problems. And the list of citations is way too long. But what you should be thinking of from this theorem is that you wouldn't expect non-unique behavior if you have some analyticity involved. And so the C infinity nature of our target manifold is important. And we're going to talk about that now. There are C infinity functions which vanish to infinite order, so they don't satisfy the Voya inequality. Just going back for a second, this gamma sort of encapsulates the order to which f vanishes at x0. So here's an example of a C infinity function which vanishes to infinite order. You could have come up with one yourself, I'm sure. And as a corollary, that means that there exists C infinity functions such that the gradient flow is bounded but doesn't have a limit as t goes to infinity. And Leon Simon's green book has this very beautiful example of what he calls goat tracks. So the goat walks up the mountain along this gradient flow, but every point of this curve gamma is a limit point as time goes to infinity. Okay. So maybe you say, okay, Max, you've sort of given away the game here. We know how this works in the parabolic setting. And so you're just going to do the exact same thing in the wave map setting. And I would say, yes, sure. But one has to be really careful when you apply these sort of parabolic lessons to Hamiltonian PDEs. And so let me give you a couple of ODE examples. It's not true that if you have an analytic sort of potential, then you have long-term, a long time limit, right? One of the simplest analytic potentials is this F that I've right here. But if you look at the Hamiltonian flow, so I'm taking 2 time derivatives, then actually you circle around the unit circle, right? And so you don't have a limit as time goes to infinity. Similarly, critical points are not barriers. So if you look at this function F, which you should think of as sort of being the function whose gradient flow I showed you on the previous slide, this goat tracks example, the parabolic flow has as its limits all points on the unit circle as t goes to infinity. But the corresponding Hamiltonian flow doesn't limit to any point on the unit circle as t goes to infinity. And this is because in the parabolic setting, the unit circle is a barrier, which means that you hit it and then you stay there. Whereas in the Hamiltonian setting, you can go in and out of the unit circle, right? There are no barriers, there's no maximum principle. And so it's sort of not true to say that you should be able to take any lessons you know about the long-term time limit of parabolic flows and apply them to Hamiltonian flows. Okay, so now let me give you a couple details about the proof. Let me talk about the target manifold that we use. So it's this twisted product, and the metric is given by, this is the metric on the T component, and this is the standard metric on the sphere. And we pick the metric on the T component so that this curve gamma, which I'll draw in a second, is going to be a geodesic. And we can do this analytically. That's no problem. And gamma winds around W equals 0 infinitely many times as S goes to plus and minus infinity. And something you should notice is that the gradient of F, or sorry, why would you notice this? We construct F such that its gradient is always parallel to gamma, and that its minimum occurs on W equals 0, and that F is bounded. And these 3 things together are only possible if F is non-analytic, right? You can't have a gradient of an analytic function which is parallel to an infinite length geodesic, but which is sort of bounded as time goes to infinity. It's sort of, yeah, it will violate the Voya-Savage inequality, essentially. And these 2 facts are important because it means that if you look at the twisted product of gamma and the sphere, it lies what's called totally geodesically inside of the manifold, which means that if you start a flow inside of this geodesic, it will stay inside of the geodesic for all times. So this is how we constrain the flow. And Topic's manifold is very similar. So let me sort of draw, this is my T2 component. And you should think of gamma as, so this is W equals 0. This is W, and this is Z. Gamma is sort of doing this. I mean, okay, this is bad, right? Because it goes in here and then comes out here, right? Because it's a torus. And it is winding around infinitely often as I'm going down to W equals 0. And similarly, it starts winding around infinitely often as I go up to W equals 1, which is the same point as W equals 0. Cool. Okay, maybe I'll skip this sort of little comment because we're running a little bit low on time. So let me talk to you a little bit about Topping's definition of winding, which is how he proves non-uniqueness. He says that a singularity is winding if you have this sort of bubble when you look at the map going into the manifold, but that if you lift the map to the manifold's universal cover, you don't have a convergent subsequence, right? And what Topping observed in the setting of harmonic map heat flow, but works the same for wave maps, is that if you have a winding singularity, you can't expect to have a sort of bubble tree which holds for all time, or you can't expect to have continuous time Soliton resolution. And that's because if you had continuous time Soliton resolution, it should also lift to the universal cover, but then this assumption of no convergent subsequence would contradict that. So we're going to look at a particular harmonic map, which is going to be 0 in the W component, a constant in the Z component, and then our old friend, the ground state, in the alpha component. And we're going to show that you can get this W as a bubble for every value of Z between 0 and 1. So this is the continuum of harmonic maps, all of which have the same energy for our manifold. So it's not particularly hard to show that if you see one of these bubbles as a limit, then in fact you have to see all of these bubbles. The singularity is winding. And that's because you have to travel all the way around omega, right? To sort of get to a point here, 0 Z naught, you would have to have gone around gamma so many times, which means you got close to every other point on the bottom also. Okay. Do I have 50 minutes or an hour?
An hour.
Oh,
An hour.
I don't know why I'm rushing. I apologize. Okay, great. So maybe let me go back. Is this sort of picture a little bit clear? Are there any questions about what's going on here? Of course, it's hard to visualize, but somehow this awfully drawn schematic is what you should be thinking. So it's the same bubble in the sphere component, but it's just that the torus component wraps around over and over and over again. And that's why you see sort of a continuum of bubbles in the limit. And if you lifted this to the universal cover, you would see that these bubbles would sort of go off to infinity, right? Because this gamma, when you lift it to the universal cover, is unbounded. It represents a non-torsion element in pi1. These are words I learned from my algebraic topology friends. So, okay. So let me talk about this winding for a second. It's actually quite hard to prove non-uniqueness, which is why this is a really nice idea from Topping. There are several tools to prove that you have to blow up to something. Topology is a big one. You can show that there are sort of no topologically non-trivial harmonic maps, and so if you can't exist for infinite time, and that means that you have to have blown up and changed the topology or something like this. These are sort of the usual tools. But there are very few tools to prove that you blow up to a specific bubble. So, you know, if I want to say I blow up to this particular omega, the only way I know how to do it is that you sort of form an ansatz around omega, and then you try to use some fixed point theorem or some linearization to complete the solution around it. This is sort of how the Krieger-Schlag-Tataru blow-up result works. There are also some gluing constructions, but these constructions only work if the bubble is unique. So it's actually very hard to construct a flow which blows up to two different specific bubbles, right? You can show the flow blows up, but it's hard to show that it blows up to two different things. This winding idea is great, but it needs some topology, which doesn't really seem like it should be necessary for non-uniqueness in general, right? If your target manifold is topologically trivial, then the universal cover is the same thing as the manifold, which means that you're not going to get anything out of winding. And this winding only captures one type of non-uniqueness, which is the type of non-uniqueness where the image of the bubble changes. But you could imagine that you have two different bubbles, right? Omega 1 and omega 2, and they look like this at one time, but then they switch places at a different time, right? So in particular, if you have Q1, which is x over lambda 1t, and Q2, x over lambda 2t, you can imagine a situation where lambda 1 is bigger than lambda 2 along Tn going up to T max, but lambda 2 is much bigger than lambda 1 if Sn goes up to T max. And this is a type of non-uniqueness which wouldn't be encapsulated by winding. So, you know, this is a really nice idea, but there's still a lot of big questions about how non-uniqueness can occur. There's a very beautiful recent result by Ducaerts, Koenig, and Merle, which shows that this type of switching can't occur for the nonlinear wave equation. They basically show that each switch costs you some amount of quantized energy, and so it can't happen infinitely many times. Okay, so let me give you a sort of big sketch of the proof. And in red, I'll indicate complications that didn't exist for topping, but that do exist for us. Okay, so we construct the manifold, which I've talked to you about before, and we take smooth initial conditions, which are contained in the tangent bundle over gamma cross S2. And we do this because that means that you should, because this submanifold lies nicely inside of the large manifold, the flow should be contained in this submanifold for all time. So sorry. One additional difficulty we have here is that Peter topping can constrain the flow using the maximum principle. Whereas for us, we don't have a maximum principle. So we need to find the metric twist globally on our manifold. And this creates a whole host of technical problems, which is a pain. Step 2 is we need to show energy concentration. So Sturbins-Dutaru tells us that for finite time, one of two things happens. Either you bubble or you can keep going. But there's this problem at infinite time that maybe you do this thing called scattering, right? Where the energy disperses. So we need to show that energy concentrates if we make it all the way to infinite time. And we do this by using the fact that the alpha component is going to be non-trivial. So the fact that the alpha component wraps all the way around the sphere will prevent this energy dispersion. And this was first observed by a very nice paper in Christodoulou and Tablodarzada in '93. But of course, we had to adapt it to our setting. For topping setting of harmonic map heat flow, you can immediately guarantee that bubbling happens. And in fact, you can guarantee that it happens at a specific finite time. And this is because topology rules out the bubble, the heat flow relaxing to a harmonic map, right? So in harmonic map heat flow, the analog of scattering is that you take your thing, which is sort of moving towards a harmonic map, and in the long time limit, it becomes a harmonic map. But you can use topology to rule this out for a topping setting. Our step 3 is that you want to show the flow can't leave this totally geodesic manifold without bubbling. The problem, of course, is that it's possible that you go along gamma, but then finally you hit this curve W equals 0, but that you haven't bubbled yet. And then once you hit the curve W equals 0, you've left the geodesic. And so who knows what the flow does afterwards. For topping, this isn't an issue because the curve W equals 0 is a barrier, but we don't have that. So now we know that we have a bubble. This bubble has to live inside of this sort of closure of this manifold that we care about because we didn't leave it before the bubbling time. But now we need to show that the bubble is of this form that we like. And here we use energy considerations to rule out the image of the bubble being strictly inside of gamma, right? So to draw a picture, we had this curve gamma, which was winding around. And now we want to show that the bubble really lives here at the bottom and not inside of this whole mess. And here we need to use energy considerations, whereas topping was able to do something a little bit similar. And then finally, and this is the same as in topping, and I've sort of described this before, if the bubble is winding around this gamma, then we really show that we have a winding singularity, and therefore we have non-uniqueness. Okay, so that's the sort of schematic of the proof. Thank you all very much for listening, and I hope you all stay safe out there.
Thank you. Questions?
I have a question. It might just be something I missed. But Max, your theorem is for any initial data starting on that submanifold within a certain energy regime, or is it a very okay?
Yeah, so that's sort of what I alluded to before. If you live inside the submanifold at time 0 and you're underneath this energy threshold, then our theorem works. So it gives you a whole family of data, but this data is not sort of robust under perturbation, right? If you push it off the submanifold,
Yeah, sure.
then I don't know what happens to it. Yeah, so it's not quite a generic phenomenon.
So besides the analytic assumption, is there another way to fix up these uniqueness conjectures?
Oh, yeah, it's a good question.
I mean, with topping, has anybody done anything with the topping since?
Yeah, so I think proving uniqueness of bubbling for harmonic map heat flow is a major open question. It's done under some assumptions when the target is a sphere. So I think if you have only one bubble and the target is a sphere, you can do it. But I think it's not even known if you could have multiple bubbles and the target is a sphere. So it's really quite difficult. Part of the issue is we talked about this Voya-Savage inequality, but it's quite hard to prove Voya-Savage inequalities for energy critical problems due to these sort of technical regularity issues.
It's interesting that this analyticity, which in say, not harmonic maps, but harmonic functions, did not turn out to be such a deadly thing in the work of Lugano, for example. While here you're showing it is, or topping, and you were showing that it's absolutely critical that you can't drop the analytic in this, at least some example.
Yeah, I think that is interesting. Let me give you a hand-wavy reason why you might expect this to be partially true. Loganoff is looking at eigenfunctions, which have a variational characterization. And in particular, they're minimizers for some problem, or maybe not minimizers, but most of the time, you expect them to be critical points which are more spot. And being a critical point which is just as good as having a Voya-Savage inequality. It actually gives you a Voya-Savage inequality with optimal exponent. So this is not how Loganoff proof works, obviously, but maybe that's kind of happening.
I'm just more the knee-jerk reaction of removing analytics from some kind of theorem where you've used real algebraic geometry critically, and where in that case, I think the variational people who were trying to study giving upper bounds weren't able to, where Luganoff was able to. So clearly a lot more needs to be understood when analyticity isn't.
May I make a comment?
Sure.
Because you can see, so there's something interesting already in Leon Simon works. So if you consider the harmonic maps, right? So that has that disease with Brian's example, and it's actually true even for minimizers. So critical points, not only for critical points. Even if you're a minimizer, actually, he has the same example. But if you're looking at the minimal surface equation, it doesn't matter that the target actually it's going to be regular. C something is more than enough. So I think there's a subtle difference in the following sense that So what is happening, I think, also in Sasha's work. So you have non-analyticity, but something is happening at very small scales, and sort of once you rescale, the final problem you land into is still something analytic, like it's harmonic functions on the Euclidean space, right? So structurally. Whereas, of course, these bubbles, they're always like looking at what is happening globally on the manifold, right? So you zoom into a point, but you always see some globality thing which is going on, right? So because the bubble somehow is taking place, is like wrapping around on the whole manifold, and so you can't even use sort of the information that you're like at least at the tangent level something analytic.
Yeah, that's a really good point, Camillo. I mean, maybe a very baby example of the phenomenon you're talking about is that if the wave map or the harmonic map, if its image is contained in a convex subset of the sphere or of the target manifold, then it actually cannot develop bubbles.
Yeah.
So bubbling is a global phenomenon. It can't happen sort of locally, whatever this means.
Okay, if there are no other questions, so let us thank Max again. Thank you.